get started. So welcome everyone. I'm very pleased to see some of you today. So as that hasn't changed, my name is still Sophie. I'm still at FlowMinder, and I'm very pleased to welcome you today for this final webinar of course 2 on modern data flow. So today we are going to go on a statistician journey to turn aggregates into estimates. So I've got with me Roland Hosner, who's a senior statistician at FlowMinder, and he's going to talk about how to use standard data sources and mobile phone data to produce population statistics.
Thank you, Sophie. Merci. And a warm welcome also from my side. I'm Roland Hosner. I'm senior statistician for FlowMinder. And today we'll present on the process that is involved in creating estimates from aggregates or also indicators or statistics. So generally about population inference from mobile phone data and standard data sources, and also bias adjustment, or talking about the biases that can come along or often come along with mobile phone data. I'd like to start by a general statement that is true about mobile phone data, and that is one of the key challenges that we face when analyzing data and wanting to draw conclusions about general populations. Mobile network operator subscribers are not a random sample of the population, and they also cannot be assumed to be a random sample, because we see in survey data and other data sources that mobile phone users are very different in their social demographics and other characteristics from the general population. And in that sense, MNO data, mobile phone data, are not a random sample, but a non-probability sample of the population. And that has downstream implications on all the analysis and statistics produced from them. There's a seminal article by US Professor Meng on the issue of biases in big data, which I recommend reading. And there I pulled several quotes from this article that highlight the problematic nature of big data and mobile phone data as well. It starts by putting out the question, which one should I trust more, a 1% survey with a 60% response rate, or a big data set, a self-reported administrative data set covering 80% of the population? And then goes on to conclude that there is indeed a risk in using big data sources, because we tend to overestimate the power and the quality of such data. Indeed, he argues that the bigness of such data is not about the absolute N, whether or not we have 1 million or 3 million or 5 million data points or IDs in our data set, but about the relative size of that data set regarding the population, the big N. One of the countries that we work on at FlowMinder, that I work with, is Ghana, a 30 million country, 30 million residents. And let's say you have a mobile phone data set of 3 million IDs for Ghana. Now, 3 million rows data set is quite large. It is indeed a big data set, but relative to the size of the population, it only covers around 10%. And it is this 10%, or the relative share, the relative size, that is important. And without taking the data quality of big data sets into account, we might end up in a big data paradox. We think we have high quality and highly useful data because the data are large, but compensating for quality with quantity doesn't work. Just relying on a big number per se, that doesn't guarantee that the outcome statistic is reliable or unbiased. Generally, about biases, we should also be aware that there's not just one bias of one parameter, but biases will be different for each statistic that is produced, for each outcome or target statistic. And indeed, bias is a measure of a statistic or a parameter, not of a data source. It's therefore wrong to say the data source is biased. What is generally meant is that the parameters derived by using these data sources, certain variables, will be biased. But it is often the case that a data source may include an unbiased estimate of one statistic and a biased estimate of another statistic. So this really needs to be assessed by parameter or by outcome statistic. How do we define a bias? First of all, the important distinction to be made is between two types of errors, systematic and random errors. Random errors are less problematic in the sense that we usually have a model to assess their distribution. If we draw a random sample of a certain sample size, we can calculate the range of deviation that we expect from a certain sample size. We usually assume that the expected random error on average is 0, and there are positive and negative deviations. And we know that the larger the sample size, smaller the random errors that come from sampling become. So with sufficiently large samples, we can assume these random errors to be small enough to be able to work with unbiased statistics. The other and more problematic type of error is a bias, and that is a systematic error, when the entire distribution is shifted to the left or right, positively or negatively. And these are the ones that we need to look out for, assess, and potentially mitigate. In very general terms, the bias is the difference between the estimated value and the true value. Let's say we have a mean estimate for a variable x. The bias is simply the difference between this estimate, that is mu hat x, and the true value in the population, mu x. If we now translate this into a scenario where we're using mobile phone data for estimating, and for now we're saying we're using mobile phone data only, the bias of such an estimate that is derived from mobile phone data, here I've denoted by mu hat x phone users, is the difference to the true population parameter of interest, mu x. This is so far only the notation. Now, what types of biases and what types of error can occur and usually do occur? These concepts have a long history of discussion and research in the survey research realm, but have recently also been translated and picked up by researchers working on big data. And the graph here on the left I'm showing is from one of these papers that translates it into a research application on digital trace data. There are similar frameworks now also published by other researchers. And the perspective is similar as for survey data, where there are biases or potential errors in the data are classified into two larger groups, one on the so-called measurement side and the other on the representation side. Now, the reason why I'm putting measurement here in quotation marks is that with mobile phone data, the data have not been collected for research or statistical purposes. They are collected by mobile network operators for billing purposes, and not with the aim of producing certain outcome statistics that we are interested in. So we're using this as a secondary data source. And as such, also, we are applying our measurement concepts to the data, but the data weren't collected with the aim of measuring a certain phenomenon. For example, population mobility, let's say on a daily scale. Thus, it's a bit different here, and thus using measurement with quotation marks. But the representation questions are very similar and indeed applicable also for mobile phone data. Now, on the measurement side, the biases may relate to the operationalization of a location or of mobility. Operationalization meaning the translation of a research construct or an abstract construct to a specific measurable variable. For example, the home location that we are looking for in able to identify where users are usually requires certain definitions of length of stay, stability of that length of stay in a certain location, a certain requirement on sufficient number of data points over time in order to assess that. And by using a certain and not another definition, we may actually introduce a bias in measuring something slightly different from what the true value, and in other words, the true home location of a user is. That would be a measurement error. Any data errors or artifacts in the data would also fall under the headline measurement error. That could be at any point from, and usually before we touch the data, when the data are generated at the mobile network operator. What we, for example, see from time to time in the data is that the coordinates of cell towers are wrong or are swapped, which we can easily identify by plotting cells on a map. But also wrong timestamps or missing timestamps. Indeed, data gaps may also introduce errors in the data. So this is something that is routinely done when we as analysts or researchers start using the data and run quality checks or run first possibility checks on the data and see whether they make sense or whether there are any obvious errors or inconsistencies in the data. But also decisions further down the line, for example, subsetting or discarding certain cases, for example, cells may introduce an error rather than correct it. This is always the trade-off in making decisions during the data cleaning and data analysis process. We usually aim to remove errors or mitigate errors, but by making certain decisions on which cases to keep, which cases to drop, how to operationalize concepts, we may also introduce errors. On the representation side, the big questions that we have to ask ourselves when using mobile phone data is about the population coverage of mobile phones in general, of mobile phone use. How many people, what percentage of the population is even using a mobile phone? And also thinking about all age groups. For example, children usually to a certain age do not use mobile phones, and also in the older age groups, use goes down, but also geographically within a country. And the second selection question is the MNO coverage. Not in all cases of a mobile phone data initiative do you have data from all mobile network operators, but you may only have data from one or two out of several network operators. So that introduces another selection. And then the third layer of selection is filtering cases or filtering the data for a specific use case or target statistic. For example, if your data initiative requires calculating home locations, you may have a certain set of requirements for IDs to be kept in the data set. For example, that you have regularly occurring events that allow you to calculate home location, and you would perhaps drop those IDs that only show up in a data set for 1 week, but not long enough for a monthly or annual statistic. And by subsetting, you introduce another selection layer, so to speak. Now, in short, every data processing step may introduce a bias, and all the discussed issues here, resulting in a cumulative bias of a statistic in the end. Now, it's true that some biases may cancel each other out to some degree. You will have problems of underestimation and overestimation. Some might not exactly balance out, but go in either direction. But not necessarily do they fall on opposite sides of that spectrum, and the resulting bias needs to be assessed and corrected for. All of this to say that big data alone are not really the solution and of limited use. They are of use when the interest really is in counting or analyzing or deriving statistics for a set of IDs in the mobile phone data set. So if what you're interested in is how many SIM cards have created an event, a billing event, or have shown up in a certain location in the country at a particular point in time or a particular interval, then of course using the data as is descriptively is fine. However, and I would argue in most cases, in most application cases, when your interest is in making inferences about a larger population or the general population of a country or a certain region, then you're talking about population inference, which mobile phone data are necessary for, or a necessary requirement, but they're not sufficient. In other words, you need additional data sets. So in general, it is fair to say that statistics derived from mobile phone data are often inherently biased and need to be adjusted for if the aim is population inference. Big data are only as big as their population coverage. And really importantly, this bias assessment, adjustment, population inference require standard data sources. So big data cannot replace a standard data source such as a census or a survey or register data, but they can only complement them. They can be used in combination with existing data sources, and that also means that mobile phone data shouldn't be seen as perhaps a cost-effective alternative to a census or a large survey. It's rather the case that they can come in as an additional data source and do have advantages, particularly the granularity and the timeliness of such data. Perhaps trivial, but also important to note that every context is different, every country, region, or district, and every output statistics. So there's no standard model, no standard parameters to be used. And really what is needed at the outset of designing a data initiative is to familiarize yourself with the data that are available for that particular use case, in addition to the mobile phone data that you have access to. Bias adjustment cannot reduce biases to zero, but only mitigate it. So we have to be aware that despite our best efforts, the output statistic might still be biased. And some of the use cases, and I'm quoting here, small area time series estimates using mobile phone data seem statistically utopian because there are real challenges in terms of the granularity and of the statistical methods and data triangulation approaches that would be required to produce such estimates. All this to say that it is statistically very challenging to produce reliable output statistics, and there needs to be a process of first of all, desk research and familiarizing yourself with the data landscape of a given country, of a given context, in order to find suitable methods for this approach that involves mobile phone data. I've brought some examples of specific results that we have seen in countries that we work in as FlowMinder. The graph I'm showing here on the right is for Ghana, based on a 2022 household survey that was run by Ghana Statistical Service and where we partnered with them to submit a few additional questions, for example, on population mobility. And we're also able to use questions on mobile phone use, and that allowed us to distinguish between mobile phone users and non-users, as you can see here on the graph on the right. So, for example, we asked for what percent of the population had done a 5-kilometer trip or a longer trip in the past 3 months before the survey. Now, the grand mean was 53.5%, so slightly more than half of the population had done such a trip recently. But if we disaggregate it into phone users and non-users, we can see that 60.4% of the phone users had done such a trip, whereas only 30.5% of the non-users had done such a trip. So less, almost exactly half of phone users. What this shows is that there are parameters. There are cases where there are large differences between these two populations. And if we were to use mobile phone data only, uncorrected, unadjusted, we would often overestimate mobility. Here, let's say we have a mobile phone data set, obviously from phone users, and we operationalize the same concept with these data, 5-kilometer trip. We would think that, and generalize that to the larger population, we would think that 60% of the population is doing such trips, where in reality it's only 53.5%. So we would definitely overestimate mobility. And we've run this analysis across 3 countries and a range of parameters from survey data, and have seen that mobile phone users are indeed showing on average higher mobility. And thus, usually there's an overestimate of mobility. To be fair, not all mobility indicators show such large differences. In some cases, they're positive but smaller. And then ultimately, the question is how much remaining bias are you willing to allow for an output statistics? But we do know that this mobility differential exists. And sorry, just to go back and mention one more point. We do know that mobile phone users are also different in their social demographics. They're more often male, they're more often urban, working age, with higher education than on average and higher socioeconomic status. So by now we know some of these selection effects. And that they also show higher mobility. So ideally, you have survey data from the same time period that you have mobile phone data from, and are able to assess these differences, and then also use the survey data for correction, which I'm going to come to in a few minutes. I'll be presenting here a use case for population statistics that we have produced as an example of how such bias adjustment and population inference can occur. And I'm going to talk you through this graph. What we are doing in a general model here that is applicable to multiple countries is we first start working with CDR, call data records, bilateral flows between admin regions in a country. We combine these flows with survey-derived weights, including confidence intervals for those weights, to produce bilateral flows between months and between areas in the country. Aggregate these to total inflows and total outflows by area, and then combine this with a baseline estimate for month 0 on the bottom left, and then basically use demographic accounting as a method. So starting with the baseline population, adding inflows, subtracting outflows each month iteratively to produce monthly estimates of the resident population of an admin area, subnational population estimates, taking baseline estimates often from the UN world population prospects, or the National Statistical Office, or aggregate population estimate, because we do see that counts of IDs or subscribers in a certain area are not an ideal candidate for population inference. And the reason for this I have on this graph, on this slide. So one of the outset questions is, do we use stock or flows, stock data or flow data for this population inference, or for the outcome statistic of the resident population per admin area? And something that is perhaps particularly strong in low and middle income countries that Flowminder works with, is that there are often large changes over time in the number of counts per area or stock data. This is the top graph here, the top line. Substantial fluctuations that probably do not translate into population change over time. Obviously, there are changes in market shares between providers. Let's say you have a country with 4 main providers, and one of the competitors may increase through marketing, through additional benefits, their subscriber base, thereby attracting users from another MNO, and then that share or the number of users of that other MNO goes down. This could be one of the reasons for a declining number of mobile phone users. It could also be that the network coverage has changed, or there are problems in network coverage. Cells become defunct, become damaged, either temporarily or permanently. It may also be that the total number of phone users in a country goes down. That could be the case when affordability is an issue. Or it could also be a matter of phone use, not necessarily the total numbers of users going down, but that they're using services less frequently, which in turn has an effect on the data that are generated and on the data that we use for outcome statistics. And these effects are hard to disentangle, or impossible to disentangle with only these data. You would need additional info, for example, on the number of active cells, on the number of users from competitors. This is something you can often acquire by using data from the mobile phone market regulatory authorities. But whatever the reason is, you have these larger changes over time in stock data time series. So simply weighting them up to a general population by a constant factor would create very implausible population estimates, which is the reason why we have decided to use flow data instead. Again, flows here meaning movements from month-to-month movements from one subnational area to another one. So flows of IDs per month, and those are more stable, less affected. Some of the effects are still visible. For example, if you look here in this period of the rectangle on the lower graph, you still see a certain decline, but it's not as pronounced as in the top graph. So we are using flow data, but so far here, these are still CDR aggregates, sums of IDs changing their home location from one month to the next. So these are unadjusted. Now there are several methods suggested in the literature. This is probably the final part of the presentation, but I'm showing you one in particular. And this Eurostat report by Derashevich from 2018 suggests what they call a domain level reweighting. Let's say the parameter you're interested in is here denoted by theta hat d, is measured in big data. And here would need to be corrected by 3 factors. As just explained before, one factor accounting for the differential population coverage, one factor for the differences in active users, and a third factor for the share of a particular data source. Here, this could be the MNO market share or the MNO share of a single MNO, if this is what you're using. So by factoring in and literally multiplying the CDR-derived indicator theta d, you will arrive at an adjusted estimate theta d. Some drawbacks of this domain level weighting are that they will not usually correct for the selection mechanism. They basically function as upscaling factors to a general population value. The coverage per domain may be unknown and may need to be estimated from survey data. And the same goes for the market share. What you usually have in the statistics by the regulatory authorities is the market shares on a national level. And that even per month or per quarter, that is something you can work with. But if you are interested in subnational estimates, you really need that per subnational unit or per domain D. This is what domains often refer to here. And that is not something that is publicly available. Usually, you may be able to get such data by requesting it directly from the MNOs or from the regulatory authority. But this is really crucial because, let's say your MNO of interest has a market share of 30%, then this 30% will vary across regions and across districts or admin 2, admin 3 areas across the country quite drastically. So using a national average for such corrections is usually not advisable because it introduces further bias or it masks the variation that does exist on lower levels, lower admin levels here. Specifically, what do we do then? We take this concept of domain level reweighting and apply it to CDR flow data. So in our case, monthly flows from one admin area to the next. We have the raw CDR aggregates, CDR relocation aggregates, as we call them. These are really counts of MSI at the end. They're not counts of users. So this is another correction that I'll come to in a minute. This is the original data that we can calculate from CDR data. And then we introduce basically two adjustments. We adjust for total population coverage and we adjust for the number of SIMs per user. That first adjustment, is important because this is the underlying problem of all CDR or all mobile phone data. What we are counting here is either devices or SIM cards or phone numbers. We're not counting people. And that is a different statistic, a different target population than what we're usually interested in. Usually we're interested in persons or groups of persons. And this needs a correction, and this correction requires usually survey data. Could also come from using the number of devices and the number of phone numbers or SIM cards in the data set, but this would only be a proxy. Ideally, you have a survey asking people how many SIM cards they're using and from which operators in order to allow you to calculate that adjustment factor that here is called DigiSIMs because this is from one of the providers we are using. From our experience, this adjustment factor is somewhere between 1 and 1.5. So people on average use slightly more than one SIM card from one provider, but not 2 or 3 on average in the general population. But it functions as a slight downward correction. You will usually have more IDs in your data set than persons behind these IDs using it because some people use multiple SIMs from the same provider. The second and more influential factor here is the population coverage. And the population coverage needs to be considered by area of interest. And because we're looking at flows here, flows from origin to destination, or A to B as in the formula, we need to consider the population coverage both at the origin area and at the destination area. We're using the quite involved formula with taking the geometric mean of those two population coverage shares, then the 6-month median to account for large fluctuations. But that goes a bit beyond the purpose of this webinar. And if you're interested in this, I would invite you to look at our website and our methodology reports where I explain this and all further calculations in detail. The reason why I'm showing this is to give you an example of how this can be used and how additional data sources can and should be used. In particular, the parameter here that is called DigiSims, so the number of sims per user, comes from survey data, and as I said, probably the best data source to look for, and survey data that need to be either commissioned or need to be sought out before starting on a data initiative that aims at counting or providing an estimate for persons rather than SIM cards. In general, there's still many caveats with such statistics. For our case of population statistics, we've seen that the outcome estimates strongly depend on the baseline population number, and this is often really hard to identify because there are such large differences, particularly for low and middle income countries. What is generally true of such approaches is that there are statistical limits to the granularity of the weights, because separate weights for each of these flows per admin unit would require very, very large sample sizes or even census data in order to calculate unique weights per flow. Think of, for example, a country where you have 100 admin units that you want to create estimates for. Now, if you look at flow data, origin to destination, basically any combination between any of these admin areas, you have 100 by 110,000 of such flow corridors, and then multiply this by a minimum number of 50 cases in a survey data set, you would arrive at a survey data size required that is 500,000 cases. Assuming you have a perfectly balanced data set by these flow corridors, and this is usually not the case because data sets in this regard are unbalanced. They're usually balanced by admin areas, but not combinations of admin areas. So you probably need more than 500,000 cases, and this is the magnitude of a very, very large household survey or a microcensus. And such data sets are rare and they're, of course, very expensive. If your aim is to produce time series estimates, you will need also longitudinal survey data matching the time series of the outcome statistics that you're interested in. It is not safe to assume that survey parameters do not change over time, particularly over long time series. So what you need in an accompanying data set is ideally a panel or a trend survey that follows, that is ongoing for the same time period. There's often a lack of validation data, and this is also true for many of the mobile phone data applications. Following these methods and approaches, we can produce outcome statistics, and we can assess them certainly for plausibility and compare them to other data sources in cross-validation. But validation in the sense of comparing them against known population totals or known target statistics from standard data sources is often very difficult, and often the reason why we're engaging in a mobile phone data initiative in the very beginning. It's not impossible. What is usually needed is census data collections in order to, including the same target statistics, in order to fully validate such data sources. These should come every 10 years with the census rounds, but again, are often really difficult and often delayed in low and middle income countries. But this relates back to what I said in the beginning, that mobile phone data are not a replacement, but a complementary data source to be used until, and certainly need to be taken with a grain of salt till estimates or counts from censuses are made available. And particularly in areas with low coverage of mobile phone users or of a certain MNO, flows might be underestimated, but that is generally true of other statistics derived from mobile phone data. There may be very large problems of under or overestimation in areas of a country where basically the population coverage of your data source of choice is very low. Now, this was the slide part. What I'd like to finish on here, and this also points towards the literature that I have compiled at the end of the slide deck, and of course will be shared with you, is what is the literature, what is the methodological discussion on such estimation approaches. And I really encourage you, if you're planning to or already involved in a mobile phone data initiative with the aim of population inference, to familiarize yourself with the literature and look for appropriate approaches depending on what type and what sources of data you have. Again, mobile phone data or CDR data need to be combined with available data sources. This is referred to as data triangulation, fusion, or integration. And it's not an entirely new problem because it's similar to what in survey research has been discussed for quite some time, of combining probability samples and non-probability samples for joint estimates. The discussion on methodological approaches for using big data, and particularly mobile phone data, has picked up in recent years. So there's more and more papers, methodological discussion on which approaches to use and use case applications of such approaches. What I'm going to present you here is the general methodological considerations. One of them in a paper by Rao in 2020. He says that you can understand or look at it from this perspective, that there could be three scenarios. And he specifically talked about combining mobile phone data with survey data. The first and really the best scenario is where you have your target variable, your target statistic in both samples, the mobile phone data set and the survey data set. If you have a measure of the target variable, y, and again, assuming that you have a very similar operationalization of that measure, these estimates from both samples can be combined via a data integration estimator, sometimes also referred to as a hybrid estimate. And keep in mind that this is very important because your estimate from the mobile phone data set does not cover the non-phone users, and they often behave differently and have a different characteristic than the mobile phone users. So with such an approach where you have a survey estimate and a mobile phone data estimate, you can combine it. Simplest way, weight the two estimates to arrive at a joint estimate that is representative for the population. But what if you don't have that? What if your target variable is not observed in a probability sample, so it's not in the survey, you only have it in a mobile phone data set? This can work if you have common auxiliary variables, common variables X, that you can see as predictors. But these need to be both available in the probability sample and the non-probability sample. Then you can work with propensity scores and estimate your target statistic y from the non-probability samples. And And there's a third scenario where you might have the only the non-probability sample available, but you have known population totals for your auxiliary variables X. And if you can use these auxiliary variables as predictors, then this will also work. So summarizing it in simple terms, you could work through combined estimates for Y for your target variables. You could estimate Y via X, a predictor, or you could find predictors X for where you have population totals available that you can then use in your model. Now this is the point where I'd like to ask you and get a quick feedback from you for your big data initiative. If you have one, if you are planning one, try to think of which scenario do you have? Do you have a target variable observed in both samples? Do you have the target variable not observed in probability sample, but you have common predictors X? Or do you only have the probability sample Y and known population totals, or maybe a completely different setup that I haven't shown? Take a moment to think about it and answer the Zoom poll that should have just popped up in your Zoom window. I'll give you a minute or two, and then I'll conclude with the content.
Hold on, let's just wait a bit longer. We've got 40% who participated now. We're getting there. If that's okay with you. Great.
Absolutely.
Thank you. And for those who are answering other setup, while we wait for more answers, feel free to put in the chat what it is. I'm sure Roland is very curious. Okay, we've got 46%, but we've been doing it for 2 minutes. So do you want me to stop it and share? Or no?
We're in no rush, so let's wait if we get more than 60% perhaps.
He hasn't moved for a bit now. So I don't know if we've got shy people or they're not confident answering. Yeah. He hasn't moved for 45 seconds. So I'm suggesting, Roland, we go with what we have.
Okay, yeah.
And then people can answer in the chat if they want to. Yeah.
Absolutely. Yeah. Do you want to show the results?
Yeah, I'm doing it now. Here you go. You should see them now.
Okay. So 29% or 2 persons out of 7 have said they have a target variable in both samples. 3 out of 7, 43% have said that they only have the non-probability sample and non-population totals. 1 person has said target variable not observed in the probability sample, and 1 has another setup. Okay. That's interesting to see. Basically, it shows you what realities do we have when working with such data. And it is also my experience, I would say our experience, that often you start with a mobile phone data set and don't necessarily have other sources to use. Maybe they're not available for the same time period. What is often available is population totals. Say you have from the statistical office an estimate of the number of people per region in the country, or a demographic estimate of how many men and women you have in a country, or how many children. Such population totals could be used. The challenge with demographic breakdowns, like by age and gender, is often that you don't have that in mobile phone data as a standard. Totals you'd be able to use for estimates would usually be total population estimates or count for a specific sub-region of the country. Yeah, I think a fair summary is that we're not always in the ideal setup or the ideal situation with the availability of data sets. And as I said, this is an assessment that should come at the beginning of designing a data initiative, drafting it, proposing it to partners and donors, that you scope available data sets, available data sources, or very first point, think about your target statistics. What exactly is it you're trying to measure with these data or use it for measurement? And what other data sources are available that measure the same concept? And if not, what other data sources could be used for auxiliary or predictive variables that could help with the process? Okay. There's a second framework, a more recent one, that has been produced by European statisticians as part of the MNO Minds project, that is coming to a close this year. So it's very recent. And they're asking a similar question: what type of statistical approaches can be used for population inference? And take a slightly different perspective, but actually this first one, see the note at the bottom, is very similar to domain level reweighting. The authors here call the first approach a randomization approach. You can think of it as a design-based approach, design-based statistics, so it doesn't involve a statistical model of the target statistic, but it does require dedicated survey data and parameters to be taken from the survey data. As you can see in the formula here, big N equals W times M. It's a very similar approach. You basically weight the raw count of the CDR you get by a weight derived from a survey. And the added value of the MNO data that you're using here is efficiency and reduced sample size for the outcome statistic, or of course the granularity of the CDR data. But this approach is in so far of limited use because the survey parameters that you need are target specific, and they will usually vary across space, time, and topic. So you might have these weights for this particular use case. Let's say this is the tourism statistic in Indonesia. This is a known use case where this has been endorsed by the statistics office. And let's say this is a tourism survey that you're using. Having these parameters for a tourism statistic doesn't mean you can use them also for a general population count estimate or for another application, because the weighting might be entirely different, and you might not even have the questions in the survey that would allow a different type of weighting. And again, it changes over time. Surveys are often only run as cross-sectional surveys, one-off surveys, and thus they're also specific to the time when they were collected. Also, the authors point out.
Great, thank you so much. Guys, thanks again, and I wish you all a great week.
The low granularity of the survey estimates will also limit the estimation approaches and not the granularity of the outcome estimates. Another family of approaches It's called quasi-randomization approaches, which is a model-based approach. Here, the idea is to model the selection mechanism as if the MNO data were observed based on known probabilities. This goes back to the initial comment that MNO data are not generated by a random process. It's very different from randomly sampling from a population, but it's a non-random sample, and the exact process, basically the probability of each person having or not having a mobile phone, or selecting or not selecting a certain mobile network operator, is unknown to us. We don't know the process, the statistical process. But here the idea is that if this selection mechanism can be modeled, and this relies on at least once access to the micro CDR data and Survey census microdata that enables just this statistical modeling of the selection mechanism, then you're in a good place, because then, assuming you have these variables that allow the selection mechanism modeling, this could entirely remove the need for a specialized survey if you can find a suitable model, and you can work with this model of the selection process to produce your outcome statistic. But having such access and combining such data on the micro level is difficult. For data protection reasons, for getting data in the first place, census data on the microdata level are usually restricted and kept by national statistical offices. Large house surveys, the same, are usually run by statistical offices, and micro access to CDR data is often either kept at the MNO, or for those researchers and analysts that have access to such data, they are kept under strict confidentiality and data protection measures in order not to further share or link the data. So this requires a very specific setup. That's not impossible, but difficult to arrive at. Family of approaches, the European statistics outline here is called superpopulation modeling, or simply just statistical modeling. The idea is similar as in Raoult's classification. Basically, you're trying to find a statistical model that allows you to predict your outcome statistic. This could be, that's option B here, MNO features for prediction. So assuming you have additional information in your mobile phone dataset, that could be, for example, the frequency, the number of events per month, or the number of top-ups, or perhaps social demographic information, if that is also shared by a mobile network operator. And if these features can be used for prediction, then this could also be used for statistical modeling. Data fusion is a possible approach based on the assumption that the target distribution of the target variable is the same as that of the input data. But then we're back to the question of validation and the question of whether such assumptions are warranted and can indeed be tested. And point C, geographically weighted regression, again, based on MNO counts as property variables. Basically another approach to trying to predict the outcome variables from variables that have predictive power. And for reliable and sufficiently accurate outcome statistics, that is also often very difficult to find suitable predictive variables. I'll conclude by saying that all of this is really crucial at the outset of a data initiative. because every statistic is different, every estimate is different, the national context and use cases are different. So if you're in a position to run a feasibility study or a pilot study, or start working with the data in a phase that focuses on data explanation, there's really a need to assess other available data sources, surveys, censuses, register data in parallel before designing and before committing to a specific estimate. Because it is important to assess what variables and statistics are available that could be used for the process of population inference. Again, for a specific use case, if it's already clear what the use case, what the target statistic is, you should assess the feasibility of such estimates. And that includes the option that it might not be feasible to use to provide a reliable or a valid estimate of the outcome statistic because the data source is lacking. And keep in mind that the bias adjustment will be different for each statistic in most cases. So there's not just one formula to be used, but probably depending on the outcome statistic, different data sources and thus different parameters to be used. Just a glimpse of the literature. This will all be shared with you at the end, after the end of this webinar. And I'll say thanks a lot for your interest and your patience so far. Stop sharing my screen. And
Roland, thank you so much. And I wish you all a very good rest of your day. Thanks,
also,
everyone.
thanks for me. Have a great day and see you in another setting.
Thanks. Bye, everyone.